Imagine never growing old. Imagine walking among the stars while your body and mind thrive for centuries. Could humanity escape the fragile bounds of Earth and the inevitability of death, living indefinitely among the cosmos? The dream of eternal life in space is no longer confined to science fiction. With advancements in biology, nanotechnology, artificial intelligence, and space engineering, the prospect of extending human life or even achieving quasi-immortality may be closer than we ever imagined. Today we will explore the extraordinary possibilities, the challenges, and the radical innovation that could allow humans to survive, thrive, and perhaps even live forever among the stars. The environment of space is not merely a backdrop for human exploration. It is an unprecedented laboratory for understanding life, biology, and the very mechanisms of aging. Humans evolved on Earth under the influence of gravity, atmospheric pressure, magnetic fields, and a specific spectrum of radiation. When we remove ourselves from these conditions, the human body reacts in ways both subtle and profound, revealing the fragility and adaptability of our physiology. In microgravity, muscles atrophy, bones lose density, and the cardiovascular system undergoes dramatic changes. Astronauts experience a redistribution of fluids, with blood and water moving toward the upper body and head, altering vision and cranial pressure. Even the cellular level is affected. Gene expression changes, immune function fluctuates, and the molecular machinery responsible for repair and regeneration responds differently. While many of these changes are challenges, they are also opportunities, providing insights into the mechanisms of aging, disease progression, and cellular repair that are otherwise difficult or impossible to observe on Earth. By studying the effects of space on the human body, scientists can identify intervention, therapies, and technologies that not only protect astronauts but may also extend human longevity in general, offering a roadmap for resisting the passage of time itself. The concept of space as a catalyst for human longevity extends far beyond the immediate physiological effects observed during months-long missions. Space exposes humans to conditions that accelerate certain biological processes, effectively compressing years of aging into months or even weeks. Cosmic radiation, while a hazard, acts as a natural experiment, revealing which cellular pathways are most vulnerable to damage and which are capable of repair. Microgravity, by altering bone density and muscle structure, illuminates the molecular signals involved in tissue maintenance, regeneration, and breakdown. Isolation and confined environments provide psychological and neurological data on stress, cognitive performance, and social behavior under extreme conditions. Each of these factors, radiation, gravity, environment, and social dynamics, serves as a probe into the underlying mechanisms of aging, resilience, and adaptation. By understanding how the human body responds to such extremes, researchers can develop strategies to enhance longevity, prevent degeneration, and engineer interventions that may allow humans to survive not just for decades, but potentially for centuries. The knowledge gained from studying human physiology in space has immediate applications for life extension technologies. For instance, research on muscle atrophy and bone loss in microgravity has led to advanced exercise regimens, pharmacological interventions, and biomaterials that promote regeneration. Cellular repair pathways that respond to radiation exposure can be augmented through anti-accident therapies, DNA repair enhancers, and gene editing techniques. Understanding how isolation and stress affect neuroplasticity informs the development of cognitive training, neuroprotective compounds, and artificial intelligence-assisted companions for long-term space travelers. These interventions, while developed with astronauts in mind, have profound implications for human longevity on Earth, creating a feedback loop where space exploration accelerates medical innovation and our understanding of aging. In this way, the harsh environment of space becomes a crucible for enhancing life, pushing the boundaries of what humans can endure and thrive under, and offering a glimpse of a future where the limitations imposed by biology may be dramatically reduced. Beyond the biological and medical aspects, space acts as a laboratory for understanding the physics of life and longevity on scales and in conditions impossible on Earth. Microgravity alters fluid dynamics within the body, affecting everything from cardiovascular circulation to cellular nutrient transport. Radiation, cosmic rays, and high-energy particles bombard DNA, revealing the cellular mechanisms of mutation, repair, and protection. These extreme conditions act as stress tests for human biology, highlighting the weak points and demonstrating pathways to resilience. By applying this knowledge, scientists can devise methods to enhance tissue repair, prevent age-related deterioration, and optimize metabolic efficiency. It is in these environments, far from the comforting stability of Earth, that we learn the rules of survival under conditions that may be necessary for interstellar habitation, long-duration missions, or even permanent colonization of other planets. The second keynote, which focuses on advanced medicine and anti-aging technologies, builds directly on the insights gained from studying human adaptation to space. Biotechnology, regenerative medicine, and nanotechnology are converging to create possibilities that were once the realm of science fiction. Nanobots capable of repairing cellular damage at a molecular level could patrol the human body, detecting and fixing DNA errors, removing senescent cells, and restoring tissue function. Gene therapies targeting longevity pathways, such as those that regulate telomere length or cellular repair mechanisms, could slow aging processes and reduce vulnerability to diseases. Stem cell technology provides the potential to regenerate entire organs or replace damaged tissues, effectively reversing aspects of aging. In the context of space, where the human body is exposed to accelerated stressors, these technologies are not merely speculative, they become essential for survival, creating the foundation for humans to thrive for decades, centuries, or even longer beyond Earth. The integration of these advanced medical technologies with space exploration is not a linear process. It is an exponential acceleration of capability. Microgravity research reveals weaknesses that can be addressed with gene editing, regenerative therapies, and pharmacological interventions. Radiation exposure highlights molecular vulnerabilities that can be mitigated with nanotechnology or protective gene modification. Psychological challenges, including isolation and cognitive strain, are addressed through AA-assisted behavioral therapies and neuroprotective compounds. Each challenge in the extreme environment of space acts as a catalyst for medical innovation, driving the development of techniques that enhance longevity and resilience. In this way, the space frontier functions as both a testing ground and an accelerant for technologies that may one day allow humans to achieve extraordinary lifespans, whether in orbit, on distant planets, or on Earth itself. The convergence of biology, technology, and space also raises questions about the ethical, social, and practical dimensions of extended life. If humans can live significantly longer through genetic, nanotechnological, or regenerative interventions, how do we ensure equitable access? How will societies adapt to populations with dramatically extended lifespans? In space, these questions become more acute. Long-term habitats, self-sustaining colonies, and multi-generational spacecraft require planning, governance, and social structures capable of supporting individuals who may live for centuries. The interplay between biological capability and societal infrastructure becomes critical, as the dream of extended life in space is inseparable from the practical realities of living in isolated, high-risk, and resource-limited environments. This emphasizes that achieving human longevity is not just a matter of science. It is a multidisciplinary challenge encompassing medicine, engineering, sociology, ethics, and cosmology. Finally, the study of human longevity in space represents the ultimate synergy between curiosity, exploration, and scientific progress. Space challenges human biology in ways that no terrestrial environment can, providing data that drive innovation in medicine, technology, and life extension. Microgravity, radiation, isolation, and extreme environments act as stress tests for our physiology, revealing pathways for intervention and enhancement. Advanced medicine, nanotechnology, gene editing, and regenerative therapies offer tools to exploit these insights, pushing the boundaries of what humans can achieve. Together, they suggest a future in which humans may not only survive, but thrive indefinitely, extending life far beyond the natural limits imposed by evolution on Earth. In contemplating this future, one realizes that the quest for immortality is not merely a dream of fantasy, but a tangible goal made possible by the interplay of space, science, and the indomitable human spirit. One of the most fascinating avenues for extending human life in space is the concept of cryonics and suspended animation. The idea that we could slow, pause, or even temporarily halt the biological processes that govern aging and cellular degradation opens up possibilities that were once the exclusive realm of science fiction. In the context of long-duration space travel, suspended animation could transform interstellar exploration from an impossible endeavor into a feasible one. The vast distances between stars mean that even at near-light speeds, journeys to neighboring solar systems could take decades or centuries. For humans to survive such voyages in their natural lifespans, we must either dramatically extend biological longevity or find a way to place the body in a state of stasis. Cryonics, the preservation of human tissues at extremely low temperatures, offers one such pathway. By cooling the body to temperatures where metabolic processes effectively cease, we can theoretically halt aging, cellular degradation, and the progression of disease. Advances in cryoprotectants, vitrification techniques, and revival protocols are moving this concept closer to reality, providing a foundation for future technologies that could allow humans to traverse the cosmos while suspended in a state of biological dormancy. Suspended animation is not merely about survival, it is a technology that could fundamentally alter our relationship with time. In a cryogenic state, decades could pass externally while the body remains biologically unchanged, effectively decoupling human experience from the relentless march of time. This has profound implications not only for space travel, but also for human longevity. Imagine a scenario where a traveler embarks on a multi-century mission, passing through generations of stars, while experiencing only the moments of wakefulness necessary to navigate critical stages of the journey. In this way, suspended animation bridges the gap between human lifespans and cosmic timescales, allowing exploration, colonization, and potentially eternal life in a manner compatible with the laws of biology and physics. The challenges, of course, are immense: preventing ice crystal formation, repairing cellular damage, maintaining neural integrity, and ensuring that revival is both safe and functional. Yet each incremental advance in cryonics research brings us closer to realizing a form of time-dilated existence where the boundaries of mortality are extended by technology, and where space itself becomes a medium in which life can persist far beyond earthbound limitations. Complementing the concept of biological stasis is the radical frontier of artificial intelligence and mind uploading. If the biological body imposes ultimate limits on lifespan, the mind may offer a way to transcend those boundaries. Advances in neuroscience and AI are bringing us closer to understanding consciousness at a level that could allow it to be mapped, digitized, and preserved. By creating a detailed neural map of the brain down to the synaptic connections and molecular pathways that encode memory, cognition, and personality, it becomes conceivable that human consciousness could be transferred into synthetic substrates. These could range from advanced robotic bodies capable of surviving harsh space environments to entirely digital platforms existing within quantum computers or cloud-based architectures. In this scenario, the essence of human identity, the memories, knowledge, emotions, and personality traits could persist indefinitely, unbanned from the vulnerabilities of flesh and susceptible only to the integrity of the digital medium. Mind uploading and AI integration offer more than just immortality. They provide the opportunity to evolve human cognition and experience in ways impossible within a biological body. A digital mind could navigate the vastness of space without concern for radiation, microgravity, or the limitations of metabolism. Processing speed could be vastly enhanced, memory could be expanded, and communication across light years could occur through advanced quantum networks or other theoretical methods. This approach fundamentally redefines what it means to live in space, shifting the focus from preserving the body to preserving and enhancing consciousness. It also opens new avenues for exploration, as uploaded minds could operate in environments and on timescales far removed from human perception, conducting scientific experiments, colonizing new worlds, or navigating interstellar phenomena in ways biological humans could never achieve. The ethical, philosophical, and technical implications of suspended animation and mind uploading are profound. Both approaches challenge our traditional notions of identity, mortality, and the continuity of self. In cryonics, the question arises, is the revived individual truly the same person, or merely a continuation of biological material preserved and repaired? In mind uploading, we face even more profound questions about consciousness. Is a digital copy of the mind equivalent to the original, or is it a new entity altogether? These are not merely abstract concerns, they are practical questions that will shape the future of human life in space. As we develop technologies capable of extending life, altering cognition, and preserving consciousness, society will need frameworks to address legal, moral, and psychological implications, ensuring that the pursuit of longevity and space survival is grounded in ethical responsibility. The scientific foundation for these technologies is being laid today through rigorous experimentation, mathematical modeling, and incremental technological breakthroughs. Cryonics research explores novel cryoprotectants that prevent cellular ice formation, vitrification techniques that solidify tissues without fracturing them, and revival protocols that aim to restore full physiological and neurological function. AI and neural mapping research is uncovering the architecture of human cognition, decoding memory storage, synaptic signaling, and patterns of neural connectivity. Together, these disciplines converge on the possibility of bridging biological limits with technological augmentation, providing the means to survive in space for durations previously unimaginable. Each discovery informs the next, creating a cascade of knowledge that accelerates our ability to extend life, preserve consciousness, and confront the challenges posed by interstellar distances and extreme environments. The interplay between suspended animation and digital consciousness also highlights a critical principle of the survival of humanity in space may ultimately depend on a hybrid approach. Biological preservation ensures that our bodies can survive until the technologies of longevity are perfected, while digital consciousness allows for exploration, observation, and the preservation of knowledge beyond the constraints of mortality. This dual approach maximizes flexibility and resilience, ensuring that humans, whether in flesh, mind, or a combination of both, can endure the hazards of space and the passage of time. In this vision, space is not merely a frontier to be crossed, but a domain in which life, identity, and intelligence can be perpetuated indefinitely, pushing the boundaries of evolution, biology, and physics itself. Suspended animation and mind uploading also transform the nature of exploration and adventure. Where previously interstellar travel was limited by human lifespan, these technologies expand the temporal horizon of human experience. A journey that might take centuries biologically could be condensed for consciousness or paused entirely in stasis, enabling explorers to witness phenomena unfolding over millennia. Civilizations could be designed to endure beyond single lifetimes, with knowledge, culture, and memory transmitted seamlessly across generations of digital or revived biological beings. Space itself becomes a canvas for long-duration civilization, where the pursuit of knowledge, survival, and perhaps even immortality drives the trajectory of humanity among the stars. In contemplating the integration of suspended animation and mind uploading, it becomes clear that the quest for human longevity in space is a synthesis of biology, technology, and imagination. Cryonics addresses the limitations of the body, nanotechnology repairs damage at the cellular level, and AI allows the mind to transcend biological constraints. Together, they create a framework in which humans are no longer bound by earthbound lifespans, capable of surviving, thriving, and exploring the cosmos across timescales that dwarf our natural existence. The edge of human experience, in this sense, extends to the farthest reaches of the galaxy and perhaps beyond, guided by the convergence of science and ambition. These approaches, while still in their early stages, illuminate a path toward a future where human life in space is not fleeting but enduring, not fragile but resilient, and not confined to the limits of biology, but empowered by the limitless potential of technological innovation. For humans to live indefinitely in space, the development of self-sustaining habitats is absolutely essential. Space, in its natural state, is an environment of extreme hostility, vacuum, microgravity, intense radiation, and temperatures that swing between unimaginable extremes. Any plan for human permanence beyond Earth requires constructing habitats that can replicate and in some ways surpass the protective and nurturing qualities of our own planet. These habitats must provide breathable air, potable water, adequate nutrition, controlled gravity, and protection from cosmic radiation, all while maintaining stability over decades or even centuries. The concept is not purely theoretical. Scientists and engineers have already proposed designs such as O'Neill cylinders, massive rotating space stations that create artificial gravity through centrifugal force, or orbiting domes equipped with closed-loop ecosystems capable of recycling air, water, and nutrients. These habitats are essentially self-contained planets, miniature Earths floating among the stars, where humans could thrive indefinitely if engineered correctly. The challenge lies in integrating every system, mechanical, biological, and ecological, into a cohesive structure that can endure the rigor of space, where repair opportunities are limited and failure can be catastrophic. A self-sustaining habitat must also address the fundamental challenge of food production. In microgravity, traditional agriculture is impossible. Require innovative approaches such as hydroponics, aeroponics, or genetically engineered plants designed to grow efficiently in artificial environments. Nutrient recycling becomes critical. Organic waste must be transformed into fertilizer, water must be purified and reused continuously, and energy must be harvested from solar arrays or other renewable sources. Even the psychological well-being of inhabitants depends on the presence of living systems, plants, animals, and microbial communities that replicate the complexity of Earth's ecosystems. These systems create a sense of life, growth, and continuity, which is essential for long-term habitation. When combined with advanced life support technologies, self-sustaining habitats offer a path for humans not merely to survive, but to thrive, extending the possibility of life for generations within the confines of a man-made ecosystem floating in the void of space. The construction of these habitats also forces humanity to rethink engineering and materials science at the most fundamental level. Space habitats must withstand micrometeoroid impacts, cosmic radiation, thermal fluctuations, and the stresses of rotation or structural expansion. This requires materials that are not only strong and durable, but also lightweight, self-repairing, and capable of integrating with living systems. Emerging technologies in metamaterials, smart composites, and nanotechnology may provide solutions, allowing habitats to adapt dynamically to environmental stresses, heal structural damage autonomously, and maintain internal stability without constant human intervention. In essence, these habitats become living structures capable of adjusting and responding to both external cosmic forces and internal human needs, creating an environment in which life can persist far beyond the temporal limits imposed by Earth. Equally important is the design of habitats to support human reproduction and long-term social cohesion. For humans to live indefinitely in space, multiple generations must survive, thrive, and reproduce within these artificial ecosystems. This requires careful management of genetic diversity, health monitoring, and psychological support. Isolation, confinement, and the monotony of controlled environments can create profound stress, potentially affecting both mental and physical well-being. Therefore, habitats must incorporate elements that stimulate human creativity, social interaction, and intellectual engagement. Cultural activities, educational programs, and even artificial natural spaces contribute to the maintenance of mental health, which is as critical as physical survival for long-term habitation. In this way, a self-sustaining habitat is not just an engineering marvel, it is a society in microcosm, a delicate balance of technology, biology, and social engineering that allows humans to flourish for lifetimes far removed from Earth. Complementing the development of self-sustaining habitats is the transformative potential of genetic engineering and human adaptation. Humans have evolved over millions of years to thrive under the conditions of Earth gravity, atmospheric pressure, and a protective magnetic field. Space, with its low gravity, cosmic radiation, and extreme conditions, presents a radically different environment, one for which our biology is poorly adapted. To survive indefinitely, we may need to modify ourselves at the genetic level. Advances in CRISPR and other gene editing technologies open the possibility of enhancing human resilience, repairing vulnerabilities, and optimizing physiology for space conditions. For example, genes could be targeted to improve DNA repair mechanisms, allowing cells to resist radiation-induced mutations, or to enhance bone and muscle maintenance in low gravity. Other modifications could improve metabolic efficiency, allowing humans to utilize food and energy more effectively in resource-limited environments. The possibilities extend even further into the realm of radical adaptation. Future humans may not merely survive in space, they may evolve to thrive. Imagine individuals engineered to have radiation-resistant skin, enhanced vision adapted to dim starlight, or modified circulatory systems optimized for microgravity. These adaptations could allow humans to colonize planets or moons that are otherwise hostile, transforming the universe from a barren void into a canvas for life. Genetic engineering may also be combined with regenerative medicine to replace or repair organs damaged by age, injury, or environmental stress, effectively extending the functional lifespan of humans indefinitely. By integrating biological modification with advanced medical interventions, humans could become a species capable of enduring the extremes of the cosmos, blurring the line between natural evolution and technological design. These interventions are not without ethical and societal implications. Altering human genetics raises questions about identity, equity, and consent, particularly when applied to future generations who cannot choose these modifications for themselves. Moreover, the interplay between genetic adaptation and self-sustaining habitats must be carefully managed to ensure that the engineered human population remains viable, diverse, and capable of sustaining social and cultural continuity over centuries. The challenge is not only technical but also philosophical. How do we define what it means to be human when our biology can be rewritten, our lifespan extended, and our physiology optimized for environments far removed from Earth? These are questions that must accompany the scientific and engineering challenges, ensuring that human adaptation in space enhances life, society, exploration rather than diminishing them. The combination of self-sustaining habitats and genetic adaptation creates a comprehensive framework for human longevity in space. Habitats provide the external conditions necessary for survival: air, water, food, gravity, and protection, while genetic and medical enhancements provide internal resilience, ensuring that the human body can endure and thrive under the unique stresses of space. This dual approach maximizes the chances of long-term survival and opens the possibility of quasi-immortality for individuals and civilizations alike. Beyond survival, it allows for the cultivation of knowledge, culture, and scientific achievement in environments that were once completely hostile to life. In this vision, space is not merely a frontier to be explored. It becomes a home, a laboratory, and a canvas for the extension of human existence far beyond the temporal and spatial limits of Earth. From an engineering perspective, these approaches drive innovation in closed-loop life support systems, bioregenerative ecosystems, and advanced materials capable of withstanding the stresses of space. They also push the boundaries of genetic science, regenerative medicine, and human-computer integration, creating a convergence of disciplines that has no historical precedent. Each challenge, whether ensuring oxygen circulation, recycling water, or maintaining genetic diversity, stimulates solutions that could revolutionize human life, both in space and on Earth. The lessons learned from constructing self-sustaining habitats and genetically optimizing humans are likely to yield advances in medicine, agriculture, ecology, and material science, illustrating how space exploration accelerates technological progress while simultaneously extending the boundaries of life itself. Ultimately, the development of self-sustaining habitats and human genetic adaptation transforms the dream of living indefinitely in space into a tangible scientific pursuit. By combining environmental engineering, life support systems, and biological enhancement, humans could survive for centuries, thrive in extreme conditions, and explore the universe on scales previously unimaginable. These technologies not only address the practical necessities of survival, but also redefine what it means to be human, offering the possibility of transcending the natural limits of biology. In contemplating these possibilities, one realizes that space is not merely a vacuum to be traversed. It is a frontier for life, innovation, and the expansion of human existence, where the challenges of survival catalyze unprecedented progress, and the dream of living forever becomes a scientific aspiration within reach. Sustaining human life indefinitely in space is not only a question of biology and habitat design, it is equally a challenge of energy and resource management on a scale that dwarfs any system ever engineered on Earth. Every human activity, from breathing and drinking to producing food and maintaining habitat integrity, requires energy, materials, and constant regulation. In space, these resources are finite, expensive, and often far from readily available. Solar energy, however, offers a near-limitless source of power if harnessed efficiently. In the vacuum of space, solar panels can capture energy without atmospheric interference, generating electricity far more efficiently than on Earth. Coupled with energy storage systems, advanced batteries, and possibly even nuclear reactors for deep space missions, humanity could maintain the continuous operation of life support systems, artificial gravity generators, radiation shields, and environmental controls necessary for long-term survival. Energy is the lifeblood of any sustained civilization in space. Without it, even the most sophisticated habitats would become uninhabitable and humans would remain at the mercy of the cosmos. Resource management extends beyond energy to include water, food, and materials. In a closed-loop habitat, every drop of water must be recycled, purified, and repurposed, while every organic waste product must be converted into nutrients for plants or processed into energy. Technologies such as hydroponics, aeroponics, and bioreactors allow humans to cultivate food in microgravity environments, creating self-sustaining ecosystems that mimic Earth's biosphere. Asteroids, moons, and planetary bodies may provide additional resources. Mining for metals, minerals, and water ice becomes essential for construction, maintenance, and expansion of habitats. Every kilogram of material must be carefully accounted for, every energy expenditure calculated, because in space, inefficiency is deadly. In this sense, the challenge of resource management is both technical and philosophical. It requires humans to live in a state of perpetual optimization, to interact with their environment in ways that are precise, sustainable, and harmonious with the constraints of the cosmos. The control and distribution of energy and resources also have profound implications for societal organization in space. In a self-sustaining habitat, energy allocation affects every aspect of daily life, from heating and lighting to propulsion and communication systems. Food production and recycling networks dictate population limits, growth rates, and social structures. These interdependencies require governance systems that are robust, adaptive, and capable of managing resources equitably. Unlike on Earth, where resources can be imported, extracted, or replaced, space habitats operate in isolation. Inefficiency or mismanagement can have catastrophic consequences. Therefore, the science of energy and resource management is inseparable from the science of survival itself. It is not sufficient to engineer life support systems. Humans must also learn to live within them sustainably, respecting the delicate balance that maintains life in an environment that offers no second chances. Complementing resource management is the necessity for genetic engineering and human adaptation, which directly addresses the vulnerabilities inherent in human biology. Life in space exposes humans to radiation levels that are thousands of times higher than on Earth, microgravity that weakens bones and muscles, and environmental extremes that test the limits of physiology. Genetic engineering offers the possibility of optimizing human biology to withstand these stresses, enhancing DNA repair mechanisms, bolstering immune function, and strengthening tissue resilience. Imagine individuals engineered to resist radiation-induced mutations, to maintain bone density without gravitational load, or to process nutrients more efficiently in controlled environments. These modifications are not merely enhancements, they are survival mechanisms turning the human body into an organism capable of thriving in environments far removed from Earth. The potential for adaptation also extends to reproduction and generational survival. To establish civilizations in space, humans must be capable of producing healthy offspring who inherit enhanced resilience. Genetic engineering allows for the correction of hereditary vulnerabilities, the reinforcement of resistance to environmental stressors, and the optimization of physiological systems for life in low-gravity, high-radiation, or closed-loop ecosystems. This opens the door to multi-generational space colonies, where humans can live, reproduce, and evolve in environments that were once thought entirely inhospitable. The process of adapting humanity to space is therefore both immediate and long-term. It ensures survival today while laying the foundation for civilizations that could endure for centuries or millennia, pushing the limits of life itself. Integrating genetic engineering with energy and resource management creates a synergy that maximizes human potential in space, while habitats provide the external conditions necessary for life. Genetic adaptations optimize the internal machinery of the human body to function efficiently within those environments. Together, these strategies reduce vulnerabilities, enhance resilience, and allow for sustainable growth over extended periods. They transform the human species from a fragile, earthbound organism into a durable, adaptable, and self-sufficient presence in the cosmos. This dual approach is essential because space does not forgive inefficiency or weakness. Survival depends on mastering both the environment and ourselves. The technological implications of these adaptations are profound. Life support systems can be downsized if humans require fewer resources due to metabolic optimization. Habitats can be constructed with more flexibility if the inhabitants are resistant to radiation or microgravity effects. And energy demands can be minimized when biological systems are designed to operate efficiently. In essence, genetic engineering amplifies the effectiveness of technological solutions, creating a partnership between biology and engineering that is greater than the sum of its parts. This integration not only ensures survival, but also enables humans to explore farther, endure longer, and adapt more completely to the diverse environments of space. Finally, the combination of energy mastery and human adaptation has profound philosophical and societal implications. Humanity's ability to harness resources, control energy flows, and optimized biology represents a new phase of evolution, one in which survival is intertwined with technological sophistication and ethical responsibility. Decisions about how we engineer ourselves, allocate resources, and organize space habitats will shape not only the future of individuals, but the trajectory of civilization. As humans push the boundaries of life into space, we are not merely explorers, we are architects of our own evolution, responsible for designing societies and biologically resilient populations that can endure the harsh realities of the cosmos. The challenges are immense, the stakes incomprehensibly high, but the potential is unparalleled. A future in which humans can live, thrive, and even flourish indefinitely, not confined to Earth, but as a lasting presence among the stars. As we reach the conclusion of this exploration into the possibility of humans living forever in space, it becomes clear that the dream of eternal life among the stars is no longer purely science fiction. Through the development of self-sustaining habitats, mastery over energy and resources, genetic engineering, and advanced medical technologies, humanity is learning not just to survive, but to thrive in environments once thought utterly inhospitable. The combination of biology and technology, of imagination and rigorous science, opens the door to lifespans far beyond what evolution has allowed on Earth, creating a future where humans could live, explore, and flourish across the cosmos for centuries or even longer. This is a vision of life that challenges our understanding of mortality, identity, and society, while simultaneously expanding the boundaries of knowledge and possibility. Thank you for joining me on this incredible journey into the frontiers of science, space, and human potential. Your curiosity and willingness to imagine a future beyond Earth are what make these ideas not only fascinating but truly meaningful. Together, we continue to push the limits of understanding, dreaming bigger, and looking to the stars with hope and ambition.